Let us have the welcome to lecture 18, that is a state variable working principles. So, as we discussed the lecture 17, that gives the symbols of the compartment models. Those symbols are used to represent the processes in the model. So, in this lecture we will be discussing a state variables working principles and how those symbols are used to represent the state variables working principles. The state variables, the flow from one compartment to another compartments using this compartment model symbols. So, let us discuss this one. This we will take an example of the state variables and you will see how the symbols can be used applied here to represent the flow of a particular state variables. So, let us have this one. So, you can see this the concepts of this state variable. If you see, these are the you can see the state variables are the describe the current conditions or the state of a system at a specific time. That is what we discussed about the state variables. These are the quantities. So, the quantified materials that changes over the time. So, this indicate the state of systems. A model having no more number of state variables is expected model should be a robust model. This what is the it represents the what the example in crop model, the state variables are. So, like soil water content, it is soil water content. So, it is not constant. So, that changes over time, that depends upon the rainfall, that depends upon the evaporation, depends upon the infiltration of rainwater into soils. So, that changes over time, even if the soil water content changes with different profiles. You have the layer 1, layer 2, layer 3. So, the flow of water from one layer to second layer, the third layer. So, the water content dynamic, because not only the uptake of water by the plants. So, that causes change in soil water content. Soil water content is not a constant, that changes over time. So, that is also that known as the state variables. Soil nitrogen and organic carbon. Soil nitrogen also, nitrogen is very dynamic. So, this soil nitrogen changes over time, because there is a crop uptake, there is a leaching loss of nutrient, volatilization loss of nutrients, runoff loss of nitrogen. So, soil nitrogen content changes over time. So, this is also a state variables that is used in crop model. Of course, leaf area index is already known to you. Leaf area index is not that changes with from the increases with the crop growth, reaches the peak value, and with the peak vegetative stage, then declines towards maturity. So, like the soil leaf area index, crop biomass, similarly the root weight, shoot weight, root shoot weight, that goes on increasing. Of course, crop biomass is not constant, but after maturity there is a loss if you do not harvest at the right time, but biomass goes on increasing, that changes over time. So, these are the changes in a state variable occurs through inflow and outflow. So, there is a inflow of carbohydrate, then outflow of carbohydrate. Soil water content also, that is a inflow and outflow. Inflow is your rainfall or irrigations is the inflow, that through infiltration also the rainwater or the irrigation water enter into soil. Then you have the outflow, this uptake by the crop, then there is a flow from one layer to another layers, evaporation loss, that is a percolation loss in the soil profile. So, these are the outflows. So, the change of volume of water in soil with time, with respect to time, dx by dt is the inflow minus outflow. So, these are the change in state variable that represent through inflow and outflow relationship. The values of the state variable at any given time define the status of the system, that is discussed now. So, at any point of time, that value of the state variable that represent the status, suppose you have the crop biomass, you have the root weight, stem weight, grain weight. So, at that point of time, what is the value that define the state of the system? Soil water content. So, at a point of today also with time that changes. So, what is the value of the soil water content? Volumetric water content, we can say gravimetric method also water content, moisture content percent. So, that indicates the value at the particular time, that indicate the state of the systems. So, these are the state variables. So, the state variables expressed are the differential equations, that is the inflow and outflow relationships. So, dxi by dt. So, state variable you can have the soil water, you can take example of biomass. If you see the soil water and the biomass. So, soil water that depends upon the rainfall, and the suppose take rainfall is the inputs and drainage the output. So, dx by dt change per time, the inflow, the rate of inflow and rate of outflow. So, if you take soil water as a state variable, the inflow is your rainfall and outflow is the drainage. So, that indicates the soil water content changes over time. If you take the biomass, crop biomass, the inflow is the photosynthesis, outflow is the respiration, because some carbohydrate lost respirations. So, the difference between the inflow and outflow, that gives the change of biomass over time. So, rate of inflow rate and outflow rate. So, this approach is used as a ensure the mass balance and the system continuity to represent the state of the systems as the state variables you can say. So, each process that is governed by the rate equations upon linear or maybe exponential provides a mathematical foundation dynamic simulation problem. So, this is what we will be explaining in this one with an example here in crop modeling. So, importance in crop modeling, how say, see the state variables are the link the biological processes to environmental conditions that dynamically you can say they track the accumulatory effects of process such as growth that lead to biomass accumulations. If you see the growth changes of growth, so that leads to biomass accumulation, developmental phases that need to phenological progress, transformation from one stage to another stage that brings this phenological process. Then resource change means you are the either the soil water contents, nutrients that go, organic carbon content that goes on changing over time. So, that these are the state variables, how they influence the systems, then the enable prediction of the crop performance at any point of time using the state variables. So, changes occur gradually reflecting real world crop response to inputs. So, like can say crop biomass changes, the d double by dt changes over time, rate of dry matter accumulations as a dry matter as a state variables. Change leaf number is a state variable that changes over time. So, change in leaf number per time, the rate of the change in leaf the node numbers, then change in soil moisture storage that changes over time ds by dt. So, this the rate of the flow or the rate change over time that can be represented for the any state variables. We have the different type of state variables in crop models like physiological variables like dry matter or the leaf area index, nitrogen uptake. So, biomass accumulations, these are the state variables. Environmental variables we have as the soil water that changes over time, temperature is not constant, that also changes over time, radiation interception also that depends upon the several parameters discussed earlier, how the radiation interception that depends upon the leaf area index, because leaf area index changes then the radiation interception also changes over time, and also the radiation input also changes over time, it is not constant. So, these are the state variables. And developmental variables, we can say the how the crop transfers from one stage to another stage, that indicates the appearance of the leaf numbers or the tiller numbers. So, developmental index and growth stage goes on as a state variables. Socio-technical, we can say in socio-technical management timing, input use, irrigation schedules. So, these are also the we can say these are some of the socio-technical indicators. So, those also changes over the time. So, each type they do interact dynamically and including the model. So, we will discuss one example of the state variables such as water tank examples. So, how then using this, how the model is represented using this Forester notation and symbols, compartment model symbols. You see that the two tanks are here, tank 1 and tank 2. So, the tank 1 has the volume of water V 1, tank 2 is the volume of water V 2. So, these are the dimension of the tank, the A 1 is the area of the tank 1 and H 1 is the height of the water in tank 1, V 1 is the volume of water in tank 1. So, F 1 to 3 is the flow rate of water from tank 1 to tank 2. and IT the inflow of water to tank 1 from source. So, this tank 1 the flow rate of water to tank 1 the inflow of water tank 1 and F 1 to T is the outflow of water from tank 1 to tank 2. So, these are the parameter dimension of the tank 1. Similarly, F 1 to T is the inflow of water to tank 2 and here the V 2 is the volume of water in tank 2, A 2 is the area of tank 2, S 2 is the height of the water in tank 2, that depends upon the volume, and O T is the output of the water outflow of water from the tank 2. So, that goes as a loss of water. So, to represent this one, you can see the what are the state variables here. The V 1 volume of water tank 1, this is a state variable, because that changes over time depending upon the inflow and outflow rate. Similarly, V 2 volume of water tank 2, this is also a state variable that changes over time, that depends upon the inflow and the outflow of water. And here the others A 2 and the H 1, these are the parameters of the tank 2, these are also A 1 and H 1 the parameter of tank 1. And this is the flow that depends the proportionality the flow of water depends upon the height of the water in tank in the tank. So, what is the change of the volume of water tank 1 with respect to time? If you see the d V 1 by dt, the V 1 is the state variable volume of water tank 1 tank 1 and change in volume of water tank 1 with respect to time. So, that is equal to the inflow rate minus outflow rate. The inflow of water minus outflow water, as we are discussing earlier, the rate of change of a state variable, that is represented by the inflow and outflow. The flow of water into tank 1 minus flow of water from tank 1 to tank 2, that indicate the change in volume of water tank 1 with respect to time per time. So, if you say IT the inflow of water in tank 1 minus F 1 to T is the outflow of water from tank 1 to tank 2 with time. And we see the flow rate of water from tank 1 tank 2, that is depends upon the height of the water. This is equal to 2 times gravitational constant height of the water above this orifice. So, flow of water from tank 1 to tank 2 is the square root of 2 times gravitational constant into height of the water above the surface, or you can say the F 1 to T is equal to C 1 the proportionality constant into 2 G H 1 the height of the water above the orifice to the power 1 by 2 the square root of the 2 G H 1. So, this is the flow rate of water from tank 1 to tank 2, that depends upon the gravitational constant and height of the water of the orifice, and that we can represent this is that means the d V 1 by dt is equal to inflow I T minus F 1 to T, and this is the C 1 F 1 C 1 2 G H 1 and H 1 height of the water, that is equal to volume by area V 1 by A 1. That means the H 1 is represented by V 1 by A 1. That means the change in volume of water in tank 1 with respect to time is equal to the inflow rate of water in tank 1 minus outflow of water from tank 1 to tank 2, and this outflow is represented by the 2 G into V 1 volume of water tank 1 by area of tank 1 to the power 1 by 2, the square root of the 2 G H 1 or 2 G V 1 by A 1. This is very clear. I hope this is clear to you. So, that means the change in volume of water tank 1 with respect to time, that is equal to the inflow of water at tank 1 minus the outflow of water from tank 1 to tank 2. Similarly, if you go to tank 2, the change in volume of water tank 2 with respect to time is the inflow of water F 1 to T minus outflow of water. So, inflow of water F1 to T, that is equal to C1 as discussed F1 to T, C1 into 2 g V 1 by A 1 to the power 1 by 2, the square root of 2 g V 1 by A 1 minus this outflow of water from tank 2 to out, that will be loss. So, that is also same way represented by this now outflow is C 2 into square root of 2 g S 2, S 2 is the height of the water above this orifice in tank 2. So, S 2 also V 2 by A 2. So, that means the d V 2 by dt is equal to the inflow of water in tank 2, that is C 1 2 g V 1 by A 1 to the power 1 by 2 minus C 2, the proportionality constant for the tank 2 into 2 g V 2 by A 2 to the power 1 by 2. So, these are the change in volume of water in tank 1 with respect to time and change in volume of water tank 2 with respect to time. So, d V 1 by dt and the d V 2 by dt. So, these are the state variables. So, now if you want to represent this as a flow chart using these Forester symbols, compartment model symbols, how does it look like? So, that we will be discussing here, how this can be represented using this flow chart. Now, you see here this is the source from where source is represented by these symbols as you have discussed earlier, and this is the rate variables and this is the IT, the flow rate inflow into tank 1 IT. So, that is represented by these rate variables. This is the rate variables, inflow is it to tank 1, the rate variables liters per hours, maybe you can liters per hours, cubic meters per hours. So, this inflow in tank 1, that is rate variables, and V 1 volume of water in tank 1, this V 1 is a state variables that changes over time, and again from V 1 to V 2, this is the rate variables F 1 to T. So, rate variable the flow rate of water from tank 1 to tank 2. If you see F 1 to T, so F 1 to T is equal to C 1 into 2 g H 1 square root or C 1 into 2 g V 1 by A 1 square root. So, these rate variables F 1 to T that depends upon C 1, these are the you can say parameters, you can C 1 that depends upon the A 1, that depends upon the V 1, that depends upon the G. So, these are the parameters that affect the rate of flow. The rate of flow from tank 1 to tank 2 is influenced by C 1, G, V 1 and A 1. So, this is how they are represented using these symbols. The A 1, C 1, G and the V 1. V 1 itself a state variable that influence the flow rate definitely, and A 1 can be a parameter, the area of the tank, C 1 is a constant and G is a universal constant, gravitational constant. So, these are the parameters and these are the state variables that influence the flow of water, flow rate of water from tank 1 to tank 2. Similarly, if you see the tank 2, the V 2 is a state variables and O T is the rate variable, flow of water from tank 1 to out. So, O T that is influenced by the parameter or the variable that influence definitely influenced by V 2, again the A 2 area of the tank 1, C 2 the proportionality constant for tank 2 and G the gravitational constant. So, these are the parameters A 2, C 2, these are the parameters, G the constants as per the we discussed about the terminology in Kraft model, what are the parameters, what are the constants. A is a parameter, C is a constant because C is a parameter, sorry, A is a parameter, C is a parameter because they are constant for a particular simulations. Parameters are remains constants for a particular simulation, but those values are likely to change when simulation condition changes. Like here A 2 and C 2 they are parameters, they are constant for a particular simulation. If your the box size changes, A 2 will change and the C 2 will also change, but the G this is a constant, this is not parameter, it is a gravitational constant that remain constant throughout. So, so how we can say here, you have the two tanks, this tank 1 and tank 2, water flow from tank 1 to tank 2 and out from the tank 2. This is represented using this the compartment model symbols. So, that gives a understanding to the users or the students. You can understand here how the inputs or the parameters they influence the flow rate, how the compartment there is a flow of from one compartment to another compartments, and what the interrelation, how do they interact with each others. So, this gives now if you see the F1 to T, the flow rate of water from tank 1 to tank 2, that depends on volume of water in tank 1, that depends upon the area of the tank 1, that depends upon the C1 the proportionality constant, and that depends upon the gravitational constant. So, these are the parameters and the variable that influence flow rate of water from tank 1 to tank 2. This is what gives understanding the input output relationship, how the flow occurs within this system. So, that gives a this is how the compartment model symbols are used to represent processes in crop model. So, this is also similar applicable for the crop model. If you see crop models, if you see this is the gross photosynthesis, this is the state variables, gross photosynthesis, and then there is a loss net photosynthesis rate of flow from net photosynthesis, then there is a final accumulation, final the gross photosynthesis rate, then net photosynthesis rates, there is a loss through respirations, carbon loss through respiration, then there is a final accumulations of this as a carbohydrate. So, we will be discussing the later classes how these symbols also used for the representing a photosynthesis and the as a transformation or the partitioning, you can say partitioning of the photosynthesis different plant how photosynthesis accumulations and partitioning we will discuss in another doing the flow charts in the coming lectures. So, this is how we represent now water tank example represent the flow of water from tank 1 tank 2 and how the compartment model symbols can be used to represent this process. And here you can say the in brief the state variables describe the you can see the current conditions of the conditions of the crop soil atmospheric systems and they change dynamically based on inflows and outflows represent through differential equations. State variables provide the core framework for modeling soil water, nutrients, crop growth and system response. The point here this using this compartment model symbols and we understand, we visualize the input output relationship, the flow, how the flow occurs, inflow and the outflow, and there is a accumulations. So, if you see the crop models, if you go to crop models in the later coming classes, you will see the carbohydrates, you can say the photosynthesis, there is a gross photosynthesis, then the respirations rate, then there is a net photosynthesis rate and that photosynthesis is converted to your the biomass accumulations. So, this is the flow rate, how the flow rate that rate of the biomass accumulations that depends upon the photosynthesis and the respiration losses. Similarly, you could go for the developmental stage also, how the developmental stages are changes over the time from one stage to another stage. So, that depends upon the accumulation of the biomass, accumulation of the thermal time. When they accumulate certain biomass, certain thermal time, certain days, the transformation from the one stage to another stage, developmental stage. That is also represented by this state variables by the rectangles. So, this lecture, so this water tank example that will give a brief understanding of the how the state variables are represented or how the processes in the model, like now this is a water tank examples. If you run the model, suppose you have the inflow of water, then outflow of water. Inflow is suppose 40 liters per hour, then the 30 liters per hour. So, if the data is available, then run the model for the 5 hours or 6 hours and you can see what is the change in volume of water in both the tanks. And if you run for certain period, then the volume of the volume of water in tank 1 will come 0 after 0 with the time. If the flow stops, flow for the certain periods, suppose you are putting the inflow in certain periods, then flow stops, then there is a increase in volume of water, then that comes down becomes 0 with time, and that indicates how the volume of water changes in tank 1, tank 2 with respect to time. So, this understanding that is represented using this the Forester notations or the you can say compartment model symbols, how that can be used to represent the flow of water from tank 1 to tank 2 and the out, and the how what are the parameters they influence the flow rate, like area or the proportionality constant C1 or the gravitational constant C1 G, how they influence the flow rate, that is also explained here. So, this is the water tank example, and also in the earlier coming classes we will discuss about some more examples of the state variables, because state variables are the you can say the backbone of any crop model, because the model having more number of state variables, that model is expected to be one of the robust and consistency models, because that represent the state of system at any point of time. So, model having more state variables, that gives a better accuracy, better predictions and the more consistent models as compared to model having less number of state variables. So, we will discuss in the coming classes the other example of state variables, how they work in this particular model. With this I thank you all.